Hello everyone and welcome back to Causality with Boris, broadcast from SobolevSpaces. In this video you will face the identification problem and I'll show you how to tackle it. Over the next chapters we take a closer look at paths in causal diagrams. Don't miss an important development on implied associations. Stick until the end of the video and watch the takeaways and compare them with your notes. Make sure to grab a PDF with extra material for this lesson. Click on the link in the description to receive it. Both covariation and causation manifest as association, lack of independence in probability terms. Covariation results from a common cause or from a stratum selection. In a sense, causation is ruled out covariation. How do we rule out covariation? We start with variables in the conditional risk models. Directed acyclic graphs tell us how to find the joint distribution for all the variables. We multiply univariate probabilities for each node given their parents. Then we derive conditional contrast between treatments given other pretreatment variables. Why pretreatment only? Well, outcomes follow treatments, and post-treatment variables can't influence the treatment choice. In fact, this means stratification on pretreatment variables. You see, we define treatment effect as an average of individual effects. Let's say every combination of variable z defines a single stratum. Then individual treatment effect is the effect of x on y in a stratum defined by values of z. Then we average treatment effects over strata distribution in the population. In fact, we average the stratum-specific difference between conditional risks. Bold P sub x refers to the marginal risk in the population where all are exposed to treatment x, and the average treatment effect is the difference in marginal risks P1 and P0. Markov condition reduces the number of variables in Z, from all pretreatment variables to only the parents of treatment. We can estimate these outcome probabilities given observed treatment in strata defined by unique combinations of parents of treatment. We label them as T here. To obtain marginal risks, we average these conditional probabilities over the study population. In this formula, Ti refers to the value that defines a single stratum, and there are a total of n of them. What if not all treatment parents are available? If some variables are not observed, then it becomes considerably challenging. Can we include other variables in a conditional probability model? Ignoring some may produce non-causal association. Do we ignore the right variables? Well, stratifying on some may produce non-causal association. Do we include the right variables? Sounds like a daunting problem. But have no fear. Here is the basic principle. We condition on variables that block all non-causal paths between treatment and outcome. Hence the identification problem. Can we block all non-causal paths? Let's say non-causal paths exist. Then treatment effect is confounded. It's confounded with the effects of other variables. And how do we identify variables for conditional probability model then? We restrict our attention to this part of the DAG. Treatment, outcome, and their ancestors, and that was proven by Lauritsen. To recap, we want to find the treatment effect, but we cannot do actual experiment. We use observations instead. And here's our identification problem: how to eliminate all non-causal association between treatment and outcome. And here's our reasoning: if non-causal associations are gone, and treatment and outcome are still associated, then there is only one explanation. That's causation between treatment and outcome. We conclude outcome is caused by treatment. In general, we get to assume only one of the two things. Either we assume that all variables are available, or we assume that we know all the dependencies. Let's say we observe all variables. We could just estimate conditional probability at each node using the regression analysis. And how do we find the joint distribution of all variables? Well, we multiply conditional probabilities together. What about the treatment effect? Well, what we do, we set treatment variable to a certain value in the joint distribution it would sever all biasing paths between treatment and outcome. Say you set x to two different values, and this leads to different distribution of outcome y, then x has an effect on y. But we don't start with observations. Our motto is concepts before data. We assume we know the dependencies among factors at play, which is a DAG. And let's say we know it. In addition to parents of treatment, there are some other pretreatment variables. For instance, ancestors of treatments and outcomes. We realistically suspect that they may produce covariation between treatment and outcome, in the absence of actual causation. Let's see what we can achieve if we know the dependencies. We find open biasing paths, then condition on nodes that block them. This identifies the causal effect, and we call it stratification. Here is a general plan to get it done. We construct a directed acyclic graph. It encodes the network of dependencies. Then we use Markov assumption and deduce implied associations. Then we determine which observable associations are causal and which are not. To identify treatment effects, we block them. And it's done by stratification on variables that block open paths. DAG is a collection of paths from treatment to outcome. And how do paths produce association between them? Well, a path is a sequence of adjacent arrows. They connect changes in two nodes, as in changes in one node cause changes in the other node, or the value of the terminal node depends on the state of the origin node. We view this dependence as association, and it is a directional association. It's implied by the direction of arrows. We believe that all associations are produced by paths, but not all paths produce association. We divide paths in causal and biasing, or non-causal in this context. What's causal path? It's a sequence of arrows going one direction from treatment to outcome. It reflects our hypothesis about how treatment exerts effect on outcome, either directly or through mediators. The total treatment effect is a product of all causal paths. All other sequences of arrows between treatment and outcome are non-causal paths, and their arrows are drawn in opposite directions. These are the paths through which other variables contribute to covariation of treatment and outcome, again, directly or through the chain of dependencies. Still, treatment effects manifest only as association. We reason on the causal nature of the association between treatment and outcome. For that, we use non-causal paths. They help us identify variables we need to control. But not all paths enable other variables to produce variation in the nodes for treatment and outcome. Recall that paths are in fact a collection of immediate effects between adjacent nodes. You saw before three nodes connected by immediate effects. They may have a configuration of arrows that make two of them independent. Causal diagrams contain two types of paths, causal and biasing. Causal path arrows always point from treatment to outcome. Biasing paths are all other sequence of arrows between the two. A biasing path is either open or closed. It's called open if contains no common effect and at least one common cause between two nodes. Open paths transmit variation from common causes to other variables. In this graph, changes in variable z may alter the value of x. It's done by changing a. The same changes in z may alter y by changing variable b. Changes in a may induce variation in x, but not in y. It's due to the direction of influence between z and I. Changes in b may induce variation in y, but not in x, since b is the immediate effect of z. Path is called closed if it contains at least one common effect for two its nodes. So closed paths do not transmit variation from other variables to treatment and outcome, because common effects block it naturally. In this graph, changes in z cannot alter variables x and y because of the direction of influence between z and a and z and b. Again, changes in a may induce variation in x but not in y, and changes in b may induce variation in y but not in x. Open biasing paths play an important role in our understanding of association between treatment and outcomes. They show how other variables may contribute to their covariation. We see an open Bayesian path between treatment and outcome, then we expect their association is non-causal. I have a term for this kind of reasoning: associational implication. Let's recap. Here's our identification problem. Eliminate all non-causal associations between treatment and outcome. My main message: it could be done by stratification on variables that block open paths. Open paths transmit variation from other variables to treatment and outcome. And if they are connected by open Bayesian paths, then you should expect non-causal association between them. Closed paths do not transmit variation from other variables. Keep on watching.